everyone. Welcome to the new format that we're going to have to kind of adapt and get used to. As you may have heard, everything's being switched to online now. And there's not a lot of resources out there for this class. You can go on YouTube and find videos, but for our, the textbook and for this course, everything that has been developed for this course has always been, taught by the previous instructor. So I can't leave you guys hanging. I want to make some videos for you to walk you through everything. Even the next video that you watch will probably be me from home with my own whiteboard making these videos. And I'll try and make like one or two videos a day, and that way you can watch them at your leisure. Obviously, the pace of the course will be adjusted a little bit. The exams are going to have to switch to like a take-home exam format. I will have more information soon, hopefully. As soon as I get more information, I will send that information along to you guys as far as the structure of the course and how everything's going to go. But in the meantime, I hope you're happy. I hope you're healthy. Stay safe. And above all, just email me if you have any questions, and I will do my best, absolute best, to help you. So this video is going to be kind of short and sweet. In class, we can get a little wordy, back and forth. Here, it's just an empty classroom. This is not my ideal situation here, but I just want to give you the section 5.5 where we talk about defining these sequences with a recursive definition. So we'll just hit that definition. I'll give you a couple examples, and then you'll be good for 5.5. Again, you can check the study guide for the types of problems. I'll have that study guide 3 posted very soon, hopefully, and then you'll see it's this section is actually going to be short and sweet. It would have been short in class as well. To kick it off, let's start with a definition for these sequences being defined recursively. And I'll try and write a little bit bigger and see if maybe one of these is a little bit darker. So we can say that a recurrence relation for a sequence, we'll call it A1, A2, A3, ... is a formula that relates. We'll talk about a general term A sub k to the previous term. We'll call that one A sub k minus 1, where k is an integer. So basically what it does, what this, the defining sequences recursively, what this relation does is it uses the previous term and then some sort of formula that has you work your way to the next term. And then you just repeat that process. Now you have your next term. You can use the formula to work your way to the next term, 8k plus 1. So the recurrence relation is probably something we've actually already encountered before somewhere. But just to start us off, here's an example. Let's say we want to define the sequence. We'll call it, just so we already used A, let's call it C1, C2, C3, ... recursively. So they'll give you some sort of formula. This will be the formula for a CK is going to be CK minus 1 plus K, plus K, CK minus 2 plus 1. So what this formula is doing is, notice it's using the previous term, CK minus 1, and it's actually using also the previous term before that one. So we need to know those first 2 terms in order to get to the third term. So what they do is they give you the first couple terms. They'll say that C1 is equal to 1, and C2 is equal to 2. All right, so this is where we step in and we say, here's our formula. And so we've got this nice formula. This is how we find those terms And then, of course, we have those previous terms now. We have C1, we have C2. So now we can start looking for the rest of the terms, and that's what this example wants us to do. After we define this, it wants us to find C3, C4, that's a dangerous one that might explode, and C5. So that's all the problem wants us to do. We erase the definition and we can work right above this and see what those next three terms are. So let's take our formula, CK, the formula to find the kth term here. We're going to use these previous terms. So what this is if I want to find C3, then K has to be 3, which means this is 3 minus 1, that's C2, we got it. This is 3 minus 2, that's C1, we've got it. But also if K is 3, I have to plug a 3 in here because there's just a K multiple here. That K is just a multiple. So let's go ahead and fill it in. C3 is going to be equal to, again, this is 3 minus 1 is C2 plus, K is 3 in this instance. C times 3 minus 2 is 1, but there's still this big plus 1, which means I'm plugging in C2, I'm plugging in C1, and then I'm computing and I'm saying this is 2 plus 3 plus 1, that's just 6. So that gives us our C3 term. Now let's look for C4, the dangerous one. Again, K is going to be 4, so that's 4 minus 1, which is C3, but I already know C3. Plus, now K is 4, so I'm replacing that K with a 4. 4 minus 2 is 2, so this is C2, and the formula just always has this plus 1 on the end. So let's plug those things in where we know C3 is 6, plus this is 4 times C2 was already given before, that's the number 2, plus 1. So 6 plus 8 plus 1 is 15. So now we've got C3, we've got C4, and then we can find C5, just to give myself a little room here. Again, there's the formula. If we want to find C5, you can see the pattern that's developing. K is 5. 5 minus 1 is C4, plus K is 5. 5 minus 2, that's C3. And then there's your plus 1. Well, we know C4, it's 15. We know C3, it's 6. So we got 15 plus 5 times 6 plus 1 to get our C5 out of the way. So this is 15 plus 30 plus 1. That's 46. I'm going to make sure you can see that. Yeah, there's a little bit of glare there. I'm trying to fight the glare. So when you define the sequence recursively, you just use this formula to keep finding the next term, the next term, the next term. But obviously you need to have a point, where you start. If the formula is going to involve previous terms, which it will because it's a recursive definition, then you need to know those previous terms. You need a place to start in order to keep developing the next term. Now let's take a look at another example. Let's see, I've got one cooked up here. That says for each integer n, greater than or equal to 1, let Cn equal 1 over n plus 1 times the quantity 2n over n. This was our choose function, right? This was like, n choose k that we talked about in the previous lecture. So this is not a fraction or something like that. That's our choose function. We want to use this to find C1 and C2. Now here's where they don't give you an initial term. They don't tell you exactly what C1 is, numerically. But given the formula, I can just replace n with 1 to get my C1. So I want to go and plug in 1 wherever I see n, because that's what I want to find. I want to find C1. So this is a fraction 1/2. 2, choose 1. Now again, be careful, we're not multiplying two fractions together. This is a very specific thing. That's 2, choose 1. Well, 2, choose 1 is just 2. All right, you can find that in your calculator, or I showed you Pascal's triangle, and but so the choose function can be computed pretty nicely. Especially this one. This is a really nice value, so it's not too scary. So this gives us. Oh, sorry, I put 2 instead of 1/2. Look at me being silly, making sure you're on your toes, huh? All right, so when I make a mistake, there's no one here to catch me, but I caught myself, which is nice. So let's find C2. So for C2, again, I'm letting n be 2, so I'm just making a nice replacement. Wherever I see n, I write 2. There's lots of n's in the formula, so we want to be careful. So let's compute this 1/3. This will be 4, choose 2. Again, we're not multiplying by a fraction. We're using the choose function. 4, choose 2, that's 6. This is 3. And so again, make sure you're going to your calculator, or however you want to compute that choose function. Make sure you're computing that choose function correctly. So again, this is an example where here's a formula, but you don't need the initial term because you can just plug in the 1, you can plug in the 2, you can plug in the 3. So this isn't relying on the previous Cn minus 1. That's the main thing there. This is not really looking for the previous term somewhere. It doesn't need to know the previous term. It just says plug in the number 1 where n is and you'll get the first term. Plug in the number 2, you'll get the second term, which is nice. And again, another example. This is probably the most popular example some can think of, and this is the Fibonacci numbers. So this is like really, really popular in the math world, and this is where we take. We'll use F for Fibonacci, just to respect him. So this is our sequence for the Fibonacci numbers. And we start this sequence out by saying F1 is 1, F2 is 1, F3 is 2. And we can keep finding more and more of these numbers. How do we do it? Well, you can see the recurrence relation that's happening here. So this sequence is defined recursively. We use the previous 2 terms. We do have to start out with some terms here because, again, fk is going to rely on 2 of the previous terms, so we need at least 2 of those to know where to get the next one. F1 and F2 can be plugged in here to get F3. Right? So I can compute F3 by simply doing F3 minus 1 plus F3 minus 2. But that is the same thing as F2 plus F1. We knew F2, that had to be given to us, plus we knew F1. All right, so you can see that I can find that third term pretty quickly. And then we can keep doing this again. If I want to compute F4, I would look for F4 minus 1 plus F4 minus 2. You can see where I can just go grab F3. I can just go grab F2 and plug them in. F3 I already found was 2, plus F2 was given to me, that's 1. So that means that F4 must be 3. And maybe just one more for fun. F5. If I want to compute F5, then obviously I need the one before it, F4, plus 2 before that one, right? F3. So adding those two previous terms together gives me F5 is going to be equal to 3 plus 2, which is 5. And so this is what we call the Fibonacci numbers, right? You add the two previous terms to get to the next term, starting with the first term is 1 and the second term is 1. And you really do need both of these 1s in order to start the sequence. So as far as defining sequences recursively, that's really, the gist of it. That's the main important part. We've looked at other sequences before. Now we want to look at sequences that have this recursive definition sort of built into them. They have this nice formula that we can use, but the formula isn't just a formula full of numbers or variables. The formula has previous terms in it. So that's why we need this recursive definition. So again, look at some of the homework, 1 through 13, 25 to 29 in the textbook. Obviously, you can just do the odds. That's a good place to get some examples, and you'll see some of those similar examples on the study guide when I post it. If you have any questions, please let me know. Otherwise, stay happy, stay healthy, and thank you very much.